IBESS, Atmospheric Systems and Pollution Management Part 8, is focused on pollution resulting from domestic and industrial waste. This is not a movie focused on atmospheric systems. Now pay close attention. I've attached Topic 8, Solid Domestic Waste, onto Topic 6, Atmospheric Systems, because solid domestic waste nicely fits within a pollution topic. The significant ideas are solid domestic waste is increasing as a result of growing human populations and consumption. Both the production and management of solid domestic waste can have significant influence on sustainability. And lastly, pollution management strategies can be applied at different levels. This slide provides an outline of all the available movies in the unit Atmospheric Systems and Pollution Management. Use this slide to find the movie you need for review. This movie is focused here on solid domestic waste. Here are two IB syllabus statements that provide important foundation when studying pollution. Pollution is the addition of a substance or an agent to the environment through human activity at a rate greater than that which the pollutant can be rendered harmless by the environment, and which has an appreciable effect on the organisms in the environment. Secondly, pollutants may be in the form of organic or inorganic substances, light, sound, or thermal energy, biological agents, or invasive species, and may derive from a wide range of human activities, including the combustion of fossil fuels. This slide helps to organize your thinking around pollution and the management of pollution. In terms of the sources of pollution, this movie is focused on the waste that comes from domestic and industrial use of goods, solid domestic waste, SDW. There are different types of solid domestic waste, the volume and composition of which changes over time. The types of solid domestic waste include plastics, paper, e-waste from computer cases, chips and cords, batteries, organic waste, packaging, construction debris, clothing, glass, and metal. Solid domestic waste is defined as garbage or refuse, discarded materials in containers, solid, liquid, or gas, resulting from industrial, commercial, mining, and from community activities, but does not include sewage or agricultural runoff. The volume and composition of solid domestic waste changes over time. You can see in this slide that paper and cardboard waste have decreased, while plastic and metals and food waste and rubber, in fact, have all increased as a percentage of the whole. One might hypothesize that the use of personal computing devices has increased the metal and plastic wastes. Electronic waste, known as e-waste, has increased tremendously in the last 20 years. This graph shows waste in millions of tons per day over time, and you can see how the quantity of waste has mirrored human population growth. So that brings us to these two IB syllabus statements. Solid domestic waste is increasing as a result of growing human populations and consumption. Both the production and management of solid domestic waste can have significant influence on sustainability, and students should be aware that for some pollutants there may be a time lag before an appreciable effect on organisms is evident. Let's now look at plastics, including the Pacific Garbage Patch. 260 million tons of plastic are released into the environment as waste every year worldwide, and 10% ends up in the ocean. In 2015, 4 million to 12 million metric tons of plastic washed offshore alone, enough to cover every foot of coastline on the planet. The Great Pacific Garbage Patch is a collection of marine debris, litter, that ends up in the oceans. The Great Pacific Garbage Patch spans waters from the west coast of North America to Japan. The Great Pacific Garbage Patch is a gyre of plastic particles moving in a circle according to the currents. The patch displays a relatively high concentration of plastic, trapped by the currents of the North Pacific Gyre, a rotation of the ocean water. The Great Pacific Garbage Patch consists primarily of suspended, often microscopic, plastic particles in the upper water column. Now let's look at waste paper. In the U.S., over 40% of municipal solid waste is paper, about 72 million tons each year. Americans use 85 million tons of paper per year, about 680 pounds per person. The average household throws away 13,000 separate pieces of paper each year. Most is packaging and junk mail. In 2011, 67% of paper consumed in the U.S. was recycled. Every ton of paper recycled saves more than 3.3 cubic yards of landfill space. Let's look at e-waste and batteries. E-waste is defined as discarded electrical and electronic equipment. E-waste has risen by 63% in just the past 5 years. E-waste includes liquid crystal displays, LCD, TV monitors, light-emitting diodes, LED, cathode ray tubes, mobile phones, photovoltaic panels, hard disk drives, etc. In 12 Asian countries, the volume of e-waste increased by nearly 2/3 between 2010 and 2015. Hong Kong, for example, produces nearly 50 pounds of digital trash per person per year. In this graph, we can see the change in e-waste over time as the number of smartphones in yellow has increased dramatically relative to desktop or laptop PCs. By 2020, there are likely to be 10 billion mobile devices in use. IB syllabus: the abundance and prevalence of non-biodegradable pollution, such as plastic, batteries, or e-waste in particular, has become a major environmental issue. Every year, approximately 30 to 50 million tons of waste, electrical, and electronic equipment, WEEE, is disposed of globally, and this number is rising by an estimated 3 to 5% annually. E-waste of significance are items that we see on the left of this pie chart: computers, cell phones, printers, and monitors. The recovery of expensive and scarce resources, such as precious metals and critical materials from e-waste, represents a significant economic opportunity. European researchers carried out an economic assessment of the recovery of materials and the potential revenue achieved, and this was 2.15 billion euros in Europe alone. The value of gold in waste, electrical, and electronic equipment is so high that it influences half of all the economic recovery potential in e-waste. Heavy metals such as cadmium, lead, mercury, nickel, and lithium can be released from waste batteries. When thrown into the household trash, batteries end up in landfills, and as the battery casing corrodes, chemicals leach into the soil and make their way into our water supply. Of the $206 billion spent on consumer electronics in the U.S. in 2012, only 29% of the resulting e-waste generated was recycled. International regulations prohibit the transboundary movement of electronic waste, e-waste, but illegal movement of e-waste to developing countries particularly is a problem. Developing countries are not well prepared to properly manage e-waste with negative externalities, particularly environmental problems related to heavy metals. Societies must make strong decisions on the collection of e-waste, particularly chips and batteries that pose a risk of heavy metal contamination. Governments must work to legislate waste collection, and proper disposal. Societies need systems legislated by government, where waste can be collected, organized, and properly disposed of. Now let's move on and take a look at a few more waste types. Let's start with organic waste types and then move from there. Organic waste is material such as food or garden and lawn clippings, but it can also include animal and plant-based material such as paper or cardboard. Organic waste is biodegradable. Biodegradable is defined as a substance capable of being decomposed relatively rapidly by bacteria or other living organisms. Organic waste can be 25 to 40% by volume of the waste stream, taking up a lot of space in landfills. Organic waste is biodegradable, but its decomposition emits methane. Now this brings us back to IB syllabus statements from the past. Food waste is prevalent in both LEDCs and MEDCs, but for different reasons. Food waste is an issue arising in MEDCs where regulatory standards may be set according to commercial preferences so that consumable food ends up being discarded when alternatives are possible. In LEDCs, food waste is an issue because of food spoilage due to poor refrigeration and poor transport infrastructure. In this graph, we can see food waste on the y-axis by region on the x-axis. Food waste during production is seen in light blue, and food waste by consumers is seen in red. There are a few things to see here. Notice how the food waste in MEDCs is generally higher than in the LEDCs, and that food waste by consumers in the MEDCs represents a larger percentage of all waste in those regions. This speaks to the high consumption and throwaway culture typical of an MEDC, but sometimes the food waste is due to food regulations in restaurants. Food waste in LEDCs comes primarily as a result of spoilage before the consumer has had a chance to purchase the food. Remember that the sustainability of food production can be increased by reducing food waste. One more time on the difference between MEDCs and LEDCs with respect to food waste. Review these ideas around food waste within the context of a unit on pollution. I'll let you study this slide on your own. Now on to packaging waste. In 2014, 163 kilograms of packaging waste was generated per person in the European Union. Paper and cardboard are the most common types of packaging waste in Europe. And glass waste. In 2006, approximately 35 billion glass containers were made in the United States, and close to 80% were beverage containers and nearly 60% were beer bottles. The remaining 20% were mostly food containers. Another 5 billion bottles were imported into the United States. For each ton of glass that is collected via recycling programs, 1,300 pounds of sand, 410 pounds of soda ash, and 380 pounds of limestone are saved, along with 2 cubic yards of landfill space. If we could recycle 50% of new glass bottles, we would save enough energy to power 22,000 homes for 1 year. And in doing so, we would be removing 181 tons of waste from landfills on a monthly basis. Construction waste. In 2013, in the U.S., of the estimated 251 million tons of consumer solid waste generated, about 40% comes from construction projects. Here is clothing waste being recycled. In the UK, clothing lasts an average of 3.3 years before a garment is discarded. Extending the life of a garment by an extra 9 months reduces its environmental impact by 20 to 30%. And last but not least of all the solid domestic waste types is the classic aluminum can. In the U.S. alone, more than 1 million tons of aluminum containers are thrown away each year. Americans throw away enough aluminum every 3 months to rebuild our entire commercial air fleet. Last year, approximately 36 billion aluminum cans were landfilled. Solid domestic waste is a huge issue worldwide because, with the exception of food and other organic matter such as yard waste, most of our solid domestic waste is not biodegradable. There are different types of solid domestic waste, the volume and composition of which changes over time. The abundance and prevalence of non-biodegradable pollution, plastic, batteries, or e-waste in particular, has become a major environmental issue. As we head toward the end of this movie, let me introduce some ideas, including a bit on the mitigation of solid domestic waste. Most of the discussion on the mitigation of solid domestic waste will be in the next movie. Here's the IB syllabus statement. There are a variety of strategies that can be used to manage solid domestic waste, influenced by culture, economics, technology, and politics. And these factors can be barriers to the proper management of waste. Do societies have the culture to recycle? Is there an economic market for recycled materials? Do societies have the technology to separate waste for the purposes of collecting materials and possibly reusing materials? Are governments legislating recycling programs and assisting in the collection process? Does the culture embrace recycling or not? Embrace composting or not? Is the government legislating programs for the recapture of materials so that waste does not end up in a landfill or in the oceans? The market for e-waste drives the economics of recycling. Without a market, reuse and recycling stops. Global e-waste markets are expected to earn almost $50 billion by 2020. It is one of the fastest growing waste streams in emerging countries as well as developed countries. The reduced lifespans of electrical and electronic consumer devices are generating large quantities of e-waste, which is growing rapidly every year. Recovered paper is a global commodity. Supply and demand for recovered paper fluctuates with the ever-changing economic conditions. Dramatic economic growth in China has fueled a very strong export demand for America's recovered paper. In 2007, approximately 35% of recovered paper was exported to overseas markets. Can we adopt a circular economy where significant quantities of our resources are recovered and reused? Resources enter the system, items of domestic use are manufactured and used, and then discarded materials are recycled and re-enter manufacturing without having to bring in new resource. This is a circular economy, and it reduces the quantity of waste. The linear economy produces waste. All resources entering the system end up exiting the system. In circular economies, resources are recycled and reused, thus requiring fewer or maybe no new resources to enter the system. The adoption of a circular economy would provide an alternative approach to waste and sustainability. Upcycling is an example of the circular economy. Bottle caps that become earrings, tire treads that become the soles of shoes, and plastic, discarded plastic, that becomes a new shopping bag. Here's another example of the circular economy where reuse of materials prevents waste. These are plastic bottles filled with water and then inserted into a tin roof, and the water with these bottles provide light when the sun is shining. Here's another example of the circular economy. Recycled plastic becomes a brick used in the construction of homes. The circular economy aims for zero waste, certainly a more sustainable solution to many of the environmental problems caused by solid domestic waste. Do societies have the technology and the cultural willingness for effective recycling? The Chinese government provides subsidies, seen as red arrows, to collectors and recyclers of materials discarded by consumers. And consumers are given money to discard waste to collectors and recyclers. Governments and economics in action to implement the circular economy. Here's an image of a government scheme in India to reduce, reuse, and recycle solid waste. The mascot of the program is the earthworm, the classic decomposer. Governments create legislation to encourage recycling and reuse initiatives. Subsidies encourage collectors and recyclers, while taxes on items not recycled encourage the consumer to recycle. Management strategies for solid waste are influenced by politics. Governments create legislation to encourage recycling and reuse initiatives. Cultures can change and adopt new lifestyle values. Government programs that provide economic incentives for reuse and recycle can develop into cultural strategies. Here is a U.S. government initiative to reduce food waste. Reduce food wasted by 50% by 2030. The Environmental Protection Agency of the U.S. government has a food waste hierarchy, a sequence of strategies from most preferred to least preferred. Reduce the amount of waste generated. Of the food waste that is generated, use the food waste to feed others, or use the food waste to feed animals, or use the food waste for industry or composting. And the last option, the food waste ends up being incinerated, burned, or ends up taking space in a landfill. Technology to incinerate waste does exist, but might there be toxic gases depending on what's being burned? More on solid waste mitigation strategies in the next movie. Technology to landfill waste does exist, but where do we find locations to put all of our trash? All of it. And could toxic compounds leak from the bottom of the landfill into the groundwater? More on solid waste mitigation strategies in the next movie. And that brings us to the end of IBESS, Atmospheric Systems and Pollution Management, Part 8.